Hello, I am Syntax here, and today we'll be looking at the second model I want to cover in this series of fundamentals of machine learning, and that will be K-nearest neighbors. So, for this video, we're going to be looking at classification. And you can see here we have two categories, the red and the blue category. And I want you just for a moment to think, why should this point be categorized as red or why it should be categorized as blue? And I think that it should be categorized to the points that are most similar to it. And by this reasoning, we can infer that it should be the neighbors, the closest points to it. Those are the most similar to it, yeah? And that would be the blue ones. They are the most similar, with 3 values being the closest to it. But here we are missing the K part of the nearest neighbors. And I want to clarify that why we could use one neighbor, and then if we use one neighbor, the red neighbor, it should be classified as red. So here kind of we have a discrepancy on what choice of K we want. And K here is a hyperparameter in K nearest neighbors. So what that means is that the value of K really depends on the problem we're trying to solve. So if we use 100 neighbors, that might smoothen things out. Our data might not even be enough, so it will take the majority of it all the time. So the K is the number of neighbors we take into account. And the K really determines if this model will be a good fit or a bad fit to our problem. And here, well, assuming we use a K of 3, and we have 2 neighbors belonging to one category and the last one belonging to another, our estimate for the category of our point is the majority. So when we have like this problem, here we went with a K of 5. We checked the 5 points, and we realized that the 5 closest points of these 3 were blue, which makes us categorize this point as blue. And now we want to look into how we calculate the distance for more than one parameter. For this problem, we were doing it in 2 dimensions only. You can imagine that we could have a 3rd dimension. Imagine like if we wanted to guess if someone was an athlete or not, you might want to take the athletic ability, the height, and more into account. So we can use this function or this equation to find out the distance between 2 points. And really, this distance is this formula is very easy to calculate. It's just a square, like the difference of squares, and then you square root that. So which makes KNN a very easy algorithm to implement, and it's what makes it one of the first machine learning algorithms to be discovered. And we also want to scale our data. So you could have a difference of 500 that doesn't mean much, since we're using millimeters. So if you had a 500 millimeter scale on maybe length, and a kilometer scale on the height, we'd get a lot of that values because the distance really isn't as well defined for these 2 variables. There's going to be the millimeters are going to be affecting it more, since the pure distance is farther away, very far away. And for this, we use standardization, and any value of standardization can work, and z-scores are a very good value of standardization, which is z is equal to x minus mu divided by the standard deviation. And finally, I want to show some code that implements K-nearest neighbors on the famous Titanic dataset to predict whether the person dies or lives. So here you can look at the code. It's very standard, and I use the K. I give a value of K from 1 to 20. So we're going to be using all of those. And we're just going to go through them and fit the KNN to the test set. We split them into test and training using a 0.8, 0.2 split. And we're going to plot them in the end. And I'm really cheating here, since I'm using the hyperparameters. I'm estimating K using the test data set. And you don't want to use this in implementation because you kind of know the data that you're going to be seeing later on, which is an error that not an error, but a simplification I used in order to explain the concept. in like standard use, you would have a validation data set that would be used for the hyperparameters. And then here is the graph that we plotted. And you can see here that we used two different scalars, the standard scalar, which is the z-score, and the min-max scalar. And you can see here for the parameter of 1, the models are very inaccurate. It's a lot big of a difference, a lot bigger of a difference than we increase the number of k. Here they have a drop, so you have to always look at the hyperparameter, is because like the difference between this and this is about like 0.08 in accuracy, just because of the hyperparameter. And here for KNN there are more hyperparameters that are included, so like how they take into account the effect if a neighbor is farther away, it'll less affect the result. But for this one, it's a very very big simplification, just for the effort of explaining this video. And you can see that our highest accuracy reaches 0.835, which is a lot higher than the baseline, which takes the majority into account, which has an accuracy of 0.59. And our model, I'd say, is very successful in using this, and even the bad hyperparameters of k equals 1 are still much better than the majority. And I really skipped through a lot of the process of the machine learning data pipeline, and it really is just to explain the model. And I hope to make a video that explains the process fully, starting from the beginning with data imputation and data filtering to get the best results out of your model. And finally, I want to end this video and thank you, and any feedback will be appreciated.